We'll start today with a concept of relation and function, or concepts of relation and functions. A relation is simply a set of ordered pairs. Let me start with a quick example, simple example. A equaling 2z, 3y, 4x, and 5w. So this is an example of a relation. It has 1, 2, 3, 4 ordered pairs. By ordered, what we mean is that we cannot switch. Once a pair is written, we may not switch the pair around. We cannot say Z2. This is 2Z, 3Y, not Y3, for instance. 4X and 5W. So there is a relation. The set of all the first coordinates is called domain. Before I continue though, so when you have a pair in a relation, so when you have, let's just label it X, Y, when you have a single pair of a relation, the first element, because they're ordered, there's a first and a second. The first one is called input, and the other one is called output. But actually, there's more than one name for them. Input, output, independent, and this one is called dependent. So there's more than one name for each one of those parts. First coordinate, second coordinate. And those are the main names for those parts of the pair. So the pair contains two parts to it. The first one is called the input, the independent, oftentimes variable, if we have a variable. In this case, we don't have a variable, it's the number 2, so it is difficult to call it independent variable. But if we had a generic variable that would represent each one of those four numbers, that variable would be the independent variable. And if we have a variable that represents each one of those four letters, that variable would be called the dependent variable. First coordinate, that's pretty clear, first and second coordinate respectively. And this makes one pair, 2, 3, 4 pairs. All right, now going back to domain. The domain of a relation, say A, is the set of all the inputs. See, that's why we need to establish the name for the parts of a pair, because otherwise I have to go back and refer to it, the first of the two numbers of the pairs. So instead of doing that, I can just have a name for them, and then we can refer to those. So the first, the domain is the set of all the inputs, 2, 3, 4, 5, and that's it. So the set contains 5, the domain contains 5 elements in it. I'm sorry, I'm mistaken. 4 elements to it. I saw the 5, so I said 5, but actually there's 1, 2, 3, 4 elements. The range of A is the set of, as you would guess, all the outputs. So second coordinates. We don't have to put them in the same order, especially since we have an alphabet order for the letters. We can start with W. So the order in which they're written here does not matter. It doesn't have to follow the same order as the order on the points. These are also called points. The pairs are called points. So we can start with W, X, Y, Z. Okay, so there is a relation, domain, and range. All right, let's have more relations. B, so more examples of relations. Say you have 2Z and 2Y. 2Z and 2Y. Before I continue, I'm using set notation, which is a set of brackets that are kind of curly, like that. Some people have a hard time drawing them. One suggestion is to draw an sort of a stretched S. So if you just look at this part, it looks like an S, and then the S backward, and that creates this. And then the S backward, and then the regular S, and that creates the other kind of bracket. So anything that is contained in between those two brackets are the elements of the set in question. Okay, so this set contains 2 points. Now, there is something interesting about this set. The domain is the set containing 2, just the number 2. That's the only, so we don't put down 2, 2. When we are drawing a set, when we are writing a set, we just write down the elements, and there's only 1, 2, even though it is repeated, we only write 1 as a set. So Z goes with 2, and so is Y. Y goes with 2. Yeah, this makes a little more sense if we have a diagram like this. So you have the domain with the single number 2, and then the range with the letters Z and Y, and then we can draw these arrows indicating that 2 goes to Z as well as 2 goes to Y. So this is another way to draw a picture of a set. And once you have it in this format, this domain makes sense because we can clearly see there's only one element. We're not going to make a copy of 2 again here. When we write out a relation with pairs, we do have to write down, because we have pairs, we don't have triples, we have to write down that Y goes with 2, just like Z goes with 2. Okay, so be careful, because these concepts are a little tricky, and we have to cement them very well in our mind, because the concept of function is very central in mathematics. We use functions extensively. So we really have to have a good grip of what a function is. The range is this set, the one that contains Z and Y. Z and Y. Sometimes I put a little hook on my Y, because otherwise it can be confused by a 4. It's not a 4, it is a Y. And that's why I also cross my Z's, so that I don't confuse them with 2's. So this is the domain, and this is the range. Okay, let's have one other example. How about 2Z and 3Z? Okay, so now this is a little bit reversed in the sense that we have 1 and 2 versus, let's see, 2 and 3. So 2, 3, and only 1 in the range, Z. Okay, so the domain, I did not write down what the domain of this is. Since B is above, we mean the domain of B, but that is not necessarily always clear. We should clarify. I'm going to put subindex B and a subindex B, meaning that this is the domain of the relation B and the range of the relation B. Okay, so domain, or we can simply write out domain of C, which will be the set that bracket kind of looks a little funny. 2, 3, 2, 3, and the range of C contains Z. Yeah, a set with only one element. Okay. All right, so all of those are relations. I have not defined what a function is. There's about 2 definitions of a function, depending on whether we start with the relation or we start without the relation. So the definition I'm going to give is the one that assumes that we already know what a relation is. But there's another definition which is broadly used in many textbooks. So, and they're equivalent. The 2 definitions are equivalent. One assumes we already know what a relation is. The other one doesn't. So since we already have the definition of relation here, we're going to go ahead and write a definition. So we define here what a relation is. We're going to define now what a function is. So definition, a function is a relation in which first coordinates do not repeat. There we go. That's it. As simple as that. First coordinates do not repeat. So let's go back to this. I see 2, 3, 4, 5. None of those repeat. There's no repetition. 2, 3, 4, and 5. And consequently, A is a function. A. Well, by A, we mean the relation A. Let's write out the relation. The relation A is a function. B, now I don't have to specify. The only reason why I put the relation is because at the beginning of a sentence, A could be misunderstood as an article. So here we mean a function. So we are saying there's such thing as function, and if there is one of it, this is the way we're going to define it. So this is an article. This gets into grammar, but we have to go into grammar a little bit. So that's why I specify that this means the relation, so we don't confuse the 2 A's. This is the set A versus the article A, as in grammatically the article. B, so I don't have to specify that this is a relation because there is no, in English, there's no article that is just the letter B. Okay, B, is that a function or not? Where is B? Oh, B is up here. Okay, so I see 2Z, 2Y. Oh, the 2 repeats. If there is only one element that repeats, that's it. That messes up the whole entire thing. So if B contained, say, 100 points, 100 of them, and one, well, actually, and 2 points having the same first input or the first coordinate, that messes up the entire set. Even if you have a million, if you have one set of pairs, one set of points in which the first coordinate is repeated, that's it. That messes up the entire thing. So there's got to be no repetition whatsoever in order for us to have a function. This is not a function. So B is not a function. Most of the things in mathematics are or are not. The sun is shining too much. So I'm going to put a block. Otherwise, we start producing shadows all over the place. So hopefully this will make things a little better. Yeah, so B is not a function. How about C? C has 2 and 3 as the first coordinates, and that's it. No more first coordinates. So that means that C is a function. C is a function. And we have to be very, very clear that we know whether something is or is not a function. Whoops. Sorry to take time to put my my box there so that the sun doesn't shine too much on the page. All right. So now let's move on to representations. Of functions. All right. So first we have the just basic set notation. And the examples are the A, B, and C that we just did. So we just put the pairs, just put the pairs here between the brackets, and that's it. If you have only a few of them, 4, 5, even 10, we can do that. That's not too much of a big deal. We have the set with conditions. Set with conditions. All right, so this is a little more sophisticated and a little more difficult. And the reason is because if you have too many elements in the set, then it is impractical to write them all. If you have 100 or 1,000 or 1,000,000 or more than that, then it becomes extremely impractical to put them all. In fact, we will have mathematically an infinite number of points in a relation. So in that case, and in a function too, it is completely impossible to write a relation in this format. So instead, okay, so let me give you an example first. Let's say we have the set D that contains 1, 2, whoops, and then like 3, 4, okay, and then let me skip a few, and 100 and 101, comma, and maybe a half and 1.5, or 1/7 and 1 1/7, or pi and pi plus 1, or even negative numbers such as -10. And can you guess what the output of this input would be under this set if we keep the same relationship? -9, for instance. Or you can have -51, comma, and -50. Okay, so after a while you start getting the idea. Oh, okay, so whatever this number is, the second component has to be one more than that, like 100, 101, a half, 1.5, 1/7, 1 1/7, pi, well, pi plus 1. One more than -10 is -9. One more than -51 is 50. So, and if we allow the inputs to be any real number, well, there's an infinity of real numbers. So this list never ends. And in fact, there's not even a way to write down a list. It is just about impossible. No, actually, it is impossible to write down a list of all those numbers. So I'm going to put some ellipses here. and then I'm gonna close it. But really, this notation is incorrect because there, we do have a sort of a pattern if we can pick it up. But then usually when we have this ellipsis, that means that we have a pattern that can be continued one element after another element after another element after another element, but we cannot really have a list, even if it's an infinite list, of all the real numbers. So this notation is actually incorrect. I'm going to make a quick note out of that. Yeah, this is incorrect because we cannot list all real numbers, comma, not even with an infinite list. Okay, so that is not practical. We can not only not practical, we cannot even achieve that. So we had to come up with a better notation, and we established this. So all the pairs x, y, okay, such that both x and y are real numbers, and y is always one more than whatever x is. Okay, so instead of writing a list, we write down an explanation. The explanation uses the pair so that we can refer back to the letters, the corresponding letters in the pair. Now, so this is workable. It's a long explanation, but it does contain every single point that we want to have. Because when we say that x is a real number, well, r, I'm using r because we're talking about x and y, but in particular, x is a real number. That includes all of the real numbers, every one of them. Okay. Now, this is very good because the explanation tells us what we have, but it is still a bit too long. So we have come up with, not me, myself, but math people have come up with a shorter notation for the same exact thing. So x, y, we use this symbol, the real number squared. So all this essentially means all the pairs of real numbers. So translate this into pairs. Well, pairs is here, and also implicit in this notation. The r squared simply means pairs, ordered pairs, x, y. So this is emphasizing that we're talking about real numbers as opposed to, for instance, integers. So this don't have to be integers. We're going to come back to that in a moment. So pairs of real numbers, that's what we're saying. Then we use a vertical line, meaning such that and instead of writing all of this, it is understood that we say, what does it say up here? Let's see, y is always one more than whatever x is. So y is one more. So that means of whatever x is. Y is one more of whatever x is. There we go. So we use this notation instead. Okay, so we go from a long list of pairs, hoping that we can figure out what the relationship is. And by the way, this is a super easy relationship. Uh, Relationships are typically not that easy in algebra and in calculus. They're actually quite complicated. This is one of the simplest ones we can have. Of course, there's a lot of simple ones. This is not the only simple one. But if the relationship was too complicated, then we wouldn't know how to pick up the pattern right away. This explanation is good. It does what it intends to do. But then we have a shorter version of the same thing, because we have so many functions to work with. It will take a while to write all of this out. Okay. Unfortunately, we get even more sloppy. Well, we get shorter, but when we get shorter, then we get a little bit more sloppy. And oftentimes, instead of writing all of this out, we just write this because this is kind of understood. All right, so we only write this. And so we have the equation notation. Equation notation, which is really, in my opinion, in my personal opinion, this is abuse of notation. But it is so widely accepted. I'm not gonna go against it, but let's admit that we are abusing the notation when we are simply writing that a function is y equals 1 plus x. Although some people might say, wait a minute, it's not, because if we use the other definition that books use, in which they bypass the relationship, they say, well, a function is a relationship, a rule that assigns inputs into outputs. So there's the rule. You got the rule. Well, it would be correct if we actually establish where x is any real number, comma, where x is any real number. Then we're okay. But again, at that point, we're beginning to extend the way we write a function or a relation. So might just as well keep it like that if we were going to extend it that much. Be as it may, we get a little lazy, and then we just start writing this. And it's understood that x can be any real number. So if we don't specify anything else, then that's it. So y equals 1 plus x represents a function. Is a little bit of abuse of notation, because really we're not even writing what x is, but in this case, it is understood that x is any, and we mean any, real number. In other words, we can, or we may use any real number for x. So that's why we do this. But in reality, if we want to be a little more proper, we should write that down. Yeah, but people accept that enough that we're not gonna change it anymore. Once people establish a pattern, if it doesn't really hurt anybody, it's not really, there's no point in changing it, other than to try to keep things very proper. But at that point, what is the point of it if it's not hurting anything? There's another way to represent graphs, rather relations, and that is with graphs. So I just want to make sure we know what we're talking about. So first, we define what a relation is. Then we define a function, what a function is. Then we went to representations. So we have this notation where you can actually list out all the points on the function, or if there are too many to even list, then we have this notation, which is kind of lengthy. This is better and proper. This is probably the best one, but we start writing and doing so many things with them. Again, this becomes very, very lengthy, even though it is a short version. Uh, so we start getting a little more sloppy, and we start simply writing this. I don't necessarily disagree. Um, as long as we know what we're talking about, I don't necessarily disagree with using this notation, as long as we understand that X can be all the real numbers. And actually there's an additional note to this. It is understood that X is any real number, or we may use any real number for X, comma, and then there's one little remark that we have to add to this, unless the formula does not allow for all real numbers. I'm going to come back to this in a little bit. Yeah, and we're getting actually, yeah, we're going to get into this in this video, but I want to leave it like that for now because I want to move on to the graphs. So if you have y equals x plus 1, so if x is 0, and then y is 1, so we have the point 0, 1, not 0, 0, that was just the origin. And then if x is 1, then y is 2. About here, we're going to have 1, 2. And then if y is 2, rather x is 2, then y is going to be 3, because remember, y is 1 more than x. In this relationship, there are many different relationships, 3. And then if x is negative 1, well, 1 more than negative 1 is 0. So we have negative 1, O, and then negative 2, negative 1, and then negative 3, negative 2, and so forth. And we have every point in between, because we could have 0.5, 1.5, which would be here, and 1/3, and 1/3, and so forth. So eventually we get all the points on this line, every single point on that line. So we put arrows indicating that this pattern continues on and on. All right, so this is the graph corresponding to this relation. Okay, most of the relations that we're going to encounter are going to be smooth. They're going to, yeah, they're going to, once you, and the reason why I'm saying that is because we may ask, how many points do I have to draw in order to start connecting the points? Well, because of smoothness and because the pattern stays the same, hopefully not too many, but in addition to that, we are learning how to identify the graph of a function by its equation. So once you look at the equation, I mean, you probably have seen this from intermediate algebra. If you have y equals mx plus b, you probably remember that that's going to be a straight line, you know, where m is the slope. You know, you can have a horizontal slope. I'm just going to use a pencil here. So you can, this has a slope of 1, slope of 0, slope of -1, and so forth. And you can have it anywhere because b tells us the y-intercept. So the y-intercept here is 1, and then you can have a y-intercept of 2, and so forth. Yep. And then we're going to get to things like y equals x squared, which is going to be, of course, a parabola. So the graph of this, see, we practice enough by doing homework and by drawing point by point initially, that we almost don't have to draw it anymore. We get to the point where we say, oh yeah, that's gonna look very much like this. We have a parabola. That's called a parabola, a straight line, and then there's gonna be other functions such as, yeah, many other functions. Um, yeah, so there's the graphical way to represent a, a function. Oftentimes, instead of writing y, there will be the need to use a formula in which the input is in the formula itself. So here, it is understood that the input is x, but there are formulas where the input is not necessarily so clear. Not to mention, we will want to manipulate the formula, and so knowing the input and the output is going to be crucial. This is what I'm trying to say. So we have the function notation, which states what the output is. So y is the output, but instead of writing the output, we're achieving two things. We're putting the input, and we're also naming the function at the same time. So when we have y1, y2, separate different functions, pretend this is y1 and this is y2, for example, it is handy to name them differently. Instead of y1 and y2, we can label it as f. This function perhaps could have a name. So this could be 1 plus x. And then we can have a second function. So 1, 2. But instead of using y1 and y2, we can refer to them as g of x equals x squared. And it will be very handy to put the input, because if we don't have the input, sometimes it is for some formulas, it could be confusing how the output come out of the input. So if we clearly state the input, which is x in this case, then it is easier to identify how the output comes about. So in this case, we're saying this notation, and let me box what I am talking about. This notation makes it clear that the way we obtain the relation is by this. The output has to be one more than the input. So this is the input. This is establishing what the input is. And so what we're going to do is add one more to the input. Here, the input is x, and the formula says that the output is going to be square whatever the input is. Yeah. I don't want to put examples yet where we don't use x, because if we bring that up too soon, it can bring confusion. But actually, by using those notations, we are clarifying things, because we are establishing explicitly what the x is. Okay, let's talk about domain again. This is getting a little, the ink in the pen sometimes causes those marks to show up on paper. Okay, let's talk about implicit domain. Implicit domain. So when we have a formula such as y equals 1 plus x, the assumption, and that's it, nothing else. Let's label this as example 1, because we're going to do a few examples. The assumption, so the implicit assumption is that the domain is the set of all real numbers. Boy, that's very lengthy to write. We usually just write domain equals from negative infinity to infinity. So we're going to be using interval notation, and that means everything. Nothing is out. Okay, so that is our domain for that function. And it is implicit because it is understood. We just write this out and we say, oh, the domain is everything. Okay. But there are times when the domain is not everything, and we have to figure out what the domain is. So for instance, let's say y equals 1 plus x over x minus 2. All right, now the domain is not everything in this case because we cannot plug in 2 into the input, into x. If we put 2 in here, we're going to end up with 3. And so 1 plus 2 is 3 divided by 0. And we may never, ever, 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 ever divide by 0. Okay? So in this case, we have to avoid the 2. Domain is from negative infinity to 2, union from 2 to infinity. So this interval notation tells us we're going to get everything. Well, the first set says all the numbers to the left of 2, and this set says all the numbers to the right of 2. So then we have all the numbers but 2. We're avoiding the 2. Okay, so if we have a number that causes the denominator to be 0, then we have to avoid it. 3. Y equals 1 plus x over x minus 2 and then x plus 2. That's another example. All right, so the domain is not going to fit here on the right, so I'm going to write it down here. The domain of this function, because this happens to be a function, is, well, we have to avoid 2, as in that case, but we also have to avoid negative 2, because if you put in negative 2 for x, negative 2 plus 2 is going to be 0, and that's going to cause the whole denominator to be 0. And we may never, ever, ever, ever divide by 0. Never, ever. So we have to do negative infinity to negative 2. We got to skip the negative 2. From negative 2 to 2, skip the 2, from 2 to infinity. And of course, we're using the union symbol to put together all of this one set. So this is one set made up by 3 sets, by 3 intervals. Now you gotta be careful. Just because there's an x in the denominator, that doesn't mean we have to start getting rid of things. Let's say you have 1 plus x. And by the way, the 1 plus x in the numerator is irrelevant. We don't really, it doesn't hurt. It doesn't add any information to evaluating the domain of the function, the 1 plus x. Okay. Oh, if we have x squared plus 1. Let me first tell you what the domain is and then explain why. So the domain of this function, again, is, notice that I'm using equal or is, equal or is, but not both, not both. We have to use one or the other, but not both. If you put equals is, that doesn't make sense grammatically. So we gotta be careful with the way we write our solutions. Anyway, it is from negative infinity to infinity. And somebody could say, wait a minute, there's an x in the denominator. Don't we have to figure out what causes the denominator to be 0? And the answer is sure, yes. However, in this case, nothing will cause the denominator to be 0. Let's think about this. When we square a quantity, even if the quantity is negative, the moment we square it, the negative, poof, disappears. It goes away. Because multiplying two negatives will give us a positive number. And even if that was 0, we will end up with 0. So no matter what input, what real number input we put in x, we will never ever get anything smaller or less than zero, nothing. So the least this quantity will be zero. In fact, when we were drawing the parabola here, um, that is kind of what we show. The output is always positive. We never go under the x-axis, implying that this output is always positive. So that's what happens here. This number is at least zero. If we add one to it, that means that the output of the denominator will be at least one. So that means that we will never, ever, ever have, in this scenario, to divide, we will never have to divide by zero. That will never happen because this denominator will never be zero. So watch out. We really have to analyze the denominator carefully. Yep, we have to slow down and figure out, okay, and think what causes this, or what could cause this to be zero. And in this case, nothing. In this case, yes. In this case, yes. So we really have to watch out. Some things do, and some things don't make the denominator zero. Something else we have to be watching, example 5, are roots. Say you have y equals the square root of x minus 7. Okay. So there's an implicit domain here. By that, we're not saying what the domain is. We ourselves have to figure out what the domain is. We cannot plug in any x value. What I mean by that, we cannot plug in every x value. If you plug in 0, we're going to end up with the square root of -7, but there's no square root of -7 within the real numbers. And we're going to assume that all the numbers are real, at least for a while. So if we don't say anything, we're assuming that all the numbers we're dealing with are real numbers. And consequently, we cannot plug in 0 or -2 because there's no square root of -9. All right, so the only way this could work is if x is greater than 7 or equal to 7. So we want x minus 7 to be greater than or equal to 0, which means that if we add 7 to both sides of the inequality, x has to be greater than or equal to 7, and then this is our domain. But we have to write it using interval notation. So we go from 7, notice that we have a square bracket because the 7 is included, comma, to infinity. All the numbers to the right of 7. So this is our domain. Domain is this set. Okay, but see, the thing is, the basic ideas of math are simple. What makes math very complicated is that the ideas get mixed up very quickly. There's many, many ways to mix the concepts in one problem very, very quickly. For instance, what if, let's put an x minus 1 on the numerator and a square root of x minus 7 in the denominator. Now you may say, well, the answer should be this because we just solved the same equation. And you would be kind of right, but not totally right. Because yes, we need the radicand, the stuff that is inside of the root, to be not negative. And that's what we are writing here. This is non-negative. By writing this inequality, we're establishing that x minus 7 cannot be a negative number. It has to be at least 0. But on top of that, this root is in the denominator. And we have to avoid dividing by 0 by all means. We may never, ever, ever divide by 0. Consequently, we have to state that x minus 7 has to be greater than 0, but not equal to 0. That means that x has to be greater than 7. And in interval notation, That means that the domain is from 7 to infinity. The difference is that this one has a bracket, this one has a parenthesis. And that is a huge difference in mathematics. Big, big difference. 7. Okay, so we had x minus 7. What about something like 12 minus x? It's not quite x minus 7. So if we had x minus 12, I would just, using the same thinking, say that the answer is from 12 to infinity. But this is not quite the same. This is x minus 7, which is not the same as 12 minus x. So let's start all over. So we want the radicand, 12 minus x, to be greater than or equal to 0. We can add x to both sides of the inequality. So 12 has to be greater than or equal to x. All right, another way to say this is that x has to be smaller than 12. So the domain is from, okay, so x has to be smaller than 12, which means to the left of 12. So we got to start with negative infinity, and then we end up with 12. All right. But then it gets more complicated. 8. What if we have square root of x minus 7 plus square root of 12 minus x? Whoa. Well, so on one hand, we're going to piggyback on example 5 and example 7. Example 5, which contains square root of x minus 7. Yep, that looks kind of, did I miss the negative? There we go. So example 5, which contains square root of x minus 7, states that the domain has to be all the numbers that are greater than 7 or equal to 7, to the right of the 7. Example 7, which contains the root of 12 minus x, says that the inputs have to be less than 12. So on one hand, the inputs have to be bigger than 7. On the other hand, the inputs have to be less than 12. But we have both conditions present in this problem. So that means that the domain has to be all the numbers starting with 7, but not beyond 12, because we have to meet both requirements. The inputs have to be bigger than 7 or equal to 7, but at the same time, they have to be no more than 12. So we have a closed interval from 7 to 12. And this gets even more complicated, or it can get more complicated. And learning algebra and mathematics in general is exactly about working through all the nuances, all the little details that come up in all of these problems and examples. So square root of 12 minus x over square root of x minus 7, for example. Okay, that's another twist. I'm going to piggyback on the previous example. Okay, so one may think, oh, so the answer has to be between 7 and 12, except that we cannot have 7 anymore, because we have to avoid 0 in the denominator. So domain equals, okay, we cannot have 7, but we start at 7, and we may have 12. See, and there is all different combinations to do this. What if we have square root of x minus 7 on the numerator, and then the square root of 12 minus x in the denominator? All right, so the domain has to go again from 7 to 12, but now we have to avoid the 12 and include the 7. Okay, And there is an infinite numbers of complicate this. What if we have square root of x minus 7 plus the square root of 12 minus x, all of that over x minus, so 7, 8, 9, 10. So let's just put a 10 there. Okay. So the numerator of this fraction looks like example 8. In example 8, we said we go from 7 to 12. And that still holds for this example. We go from 7 to 12. But we have to skip the 10 because we cannot have 10 in the denominator. Whoa. So the domain equals the set that goes from, just goofed this up, this notation, so I have to erase that. There you go. All right, it goes from 7 to 12, but skip the 10. So that means go to 10, but don't include the 10. Start again with 10 without including the 10, and then finish with 12. Whoa. Yep. Yep. There's one other example, kind of example, I have to show you, and I'm very, this is an important example. 12. A little different than all of those. Y equals quantity x plus 1, x minus 2 over x minus 2. Okay. So, and again, we're asking for the domain. Somebody could say, well, those two cancel off. So the answer is really x plus 1, and x plus 1 was one of our very, very first examples. So we may say, well, shouldn't it be all real numbers? No. So if we just looked at that, if we didn't see this part, and we were just given this, we may think that the domain is all real numbers. So again, this without where it came from would seem that we have all the real numbers. But this is something we did after the fact. This is the given problem. That's very, very important. So this is given. We simplify that. So in the given problem, there was an x minus 2 in the denominator, and we have to take that into account. It is understood that we cannot, absolutely not, use 2 for the x value. We cannot use the number 2, because if we were to put a 2 here, we would divide by 0, and under no circumstances, even if there's another 0 in the numerator, never mind that, under no circumstances whatsoever, we may divide by 0. It's prohibited. Even if there's another 0 in the numerator, somebody may think, hey, we can get, no, we cannot do that. So the domain, so let's go back to the domain. The domain is from negative infinity to 2, skip the 2, union from 2 to infinity. So we have to skip the 2 regardless of whether those two cancel or not. So the question is, okay, so how do we reconcile this with that? And the way we do that is by adding a note, comma, where x may not be 2. Okay, so whenever we are crossing things off, when we are canceling, the way we are, see, if x was 7, then x minus 2 would be 5, so we would be multiplying by 5 to then divide by 5. And multiplying by 5 and dividing by 5 undo each other. But multiplying by 0 and dividing by 0 doesn't even make sense, because we cannot even divide by 0. So no. So the way we reconcile and cross that off and cancel that off is by stating, yes, we get x plus 1, but then we have to explicitly state that x cannot be negative 2 because this x plus 1 came from this fraction. That's a tricky question, but a question that we have to know how to answer. How do we reconcile those? Simply by adding more, by being more explicit about what the domain may be. So again, if you just see x plus 1, so let me put example 13, y equals x plus 1 versus this example, they're not the same example. This is a repeat because we already saw that, but I'm writing it again next to that one. The domain goes from negative infinity to infinity. So if you just see it like that, without any other context, coming from nowhere else, we're good. But if you see it this way, yes, we simplify, but then the domain has memory. It has the memory of what we were not supposed to have to start with. So the domain retains the memory of where it came from. Yeah, very, very, very important thing with this. More about the function notation. Yeah. So example 14. This is going to be a long example. Let's say we have f of x equals our friend x plus 1, or 1 plus x, same thing. One more than the input. That's what this formula says. So the name of the function is f. This is the call name of the function. And this is the input. And the function states we're going to add 1 to the input, and that's going to be our output. Okay. Literally, you may put any number you want. So so 14a. So if you put 5, the output is, of course, 5 plus 1, which is 6. B, f of negative 1. That's a little more tricky because we're doing negative 1 plus 1, which is 0. Not too tricky. But literally, you may put anything you ever want here. C. Okay, we're assuming this is given. Okay, and we're not going to change that through this example. So what if we ask for f of x squared? Okay, so instead of x being the input is going to be literally x squared. What is the corresponding output? Well, that's why we need to understand what this formula means. This formula states, okay, whatever the input, comma, add 1 to it. So in this case, the input of this f function is x squared. Add 1 to it. There you go. Whoa. Add 1 to whatever the input is. See, when you plug in numbers, no problem. That's beginning algebra. But plugging those are more like a college algebra kind of problem. Okay. D, what if we want to plug in the square root of x? See, that's the thing. We have to get into our mind that whatever the input is for this particular function, add 1 to it. So square root of x, add 1 to it. E. Sometimes half jokingly and half not jokingly, I put a little truck, a pickup truck here. You know, that's our input. What is the output under this function? Well, the pickup truck plus 1. You may put anything in here, add 1. F. What about x plus 1 itself? Whoa. Yeah. One of the beauties, in my opinion, of math is that you can always nest things into themselves. You can compare things to themselves. I mean, this is a little bit of a side note. Whenever you say 3 is equal to 3 in math, we don't think twice about that. We write that all the time. 3 equals 3. But think about this in everyday language. If I say I am myself or I look like myself, that's kind of weird to say that. But in math, we compare things to themselves all the time. That is a common thing to do in mathematics. So if we have the formula of the output of this function as the input of the function itself, whoa, don't panic. That's why we need to know what the formula is about. The formula says add 1 to whatever the input says. So it's a good idea to translate what the formula calls to do for each input. So what is the input? X plus 1. What are we going to do to it? If you want to put parentheses, that's fine, just to keep it all together. Add 1. But then we got to simplify, of course. So x plus 1 is x plus 2. Okay, g f of 1 over x. Whoa. That is going to be, again, put this rule in your short-term memory, but not too short, in a couple-minute memory. Whatever the input is, add 1 to it. But that is exactly what this rule is telling us. So the input is 1 over x, add 1 to it. That's it. There's no more to it. There's nothing else to do with that. Yep. Yeah, don't complicate things. And by the way, it's easy to mess this up. Some people may say, oh, should that be, I'm going to put some wrong answers just to drive a point. If you put 1 plus 1, oh, that's 2 over x, that's wrong. Or if you say, well, that's 1 over x plus 1, that's wrong, because if you want to simplify this as a single fraction, let me show you how we could do that. We could change this 1 into x over x, and then combine the two now that we have the same common denominator. So we have 1 plus x in the numerator over x. So that would be a way to combine the two of them into 1. But if I don't ask you to combine 2 into 1, then you don't necessarily have to do that. Although, let's say you are working on a multiple choice problem, and this is one of the solutions. Well, we have to know that this is equivalent to that. So this would be a correct solution, as opposed to that or that. Those are wrong solutions. But that has nothing to do with the function itself. It has more to do with whether we know how to add fractions or not. Okay. Example 15. And I want to distinguish 15 from 14 by using a different letter. We don't have to use F all the time, although most of the time we use F because that is the first letter of the word function. But we can use any letter you want. So g of x. So I'm going to come up with a formula, say 3x squared minus 5x plus 7. Okay, so this is given. Yeah, we have to know what is given and what's something that is not given. So this is given in the beginning of the problem. And let's say they want us to find g of 2. Well, no problem. That is 3 times 2 squared minus 5 times 2 plus 7. Of course, that is going to be 4. 3 times 4 exponents first. While we do that, we can multiply this, minus 10 plus 7. And of course, that is going to be 12. Minus 10 is 2 plus 7. So the final answer is 9. G of 2 is 9. What about G of negative 2? Well, we've got to be a little careful with it. This is 3. Now, the input is all of that. Oh, wait. Before I do this, what I wanted to mention is, let's understand what this tells us. This tells us square the input, whatever it is, then multiply by 3 after we square. Okay, keep that on the side. Take the very same input, the very same one, multiply it by 5. Whatever it is, multiply it by 5. Then, remember the one that we put to the side? Subtract the 5 times the input from the one we put to the side. And then add 7 to all of that. So this is a very shorthand way of writing a very, very complicated thing to do with the input. So let me repeat. Take the input, square it. After we square it, we multiply by 3. Put that to the side for a moment. Grab the same input again, multiply it by 5. Bring back the one that we put to the side and subtract that minus the one we just found. Then add 7. All of that is going on here in this very, very small expression. All right, so take the 3, multiply by negative, well, actually, take the negative 2 and square it. Okay, so I'm writing down what I'm going to do, and then we're going to put that to the side. I don't necessarily have to figure this out right away, although it's not necessarily a bad idea to wait. Okay, and then we're also going to multiply those two. So remember when I said put that to the side and then figure this out, and then the one that you put to the side, subtract those two. What you could do is cook the two at the same time. You know, pretend you are cooking, a couple dishes. You don't have to cook one, finish up before you start the next one, because then maybe the food will get cold if you do that. So we're going to cook two things at the same time. So those two are cooking because we're going to subtract this guy minus this guy. So we got to wait until they're cooked before we subtract them. And then after that, we're going to add 7. So we can do that. We can sort of do two things at once. So square that. Now, this is the thing. Negative 2 squared is going to be positive 4 times 3. So I'm going a little bit fast. 3 times 4. All right. Minus, whoa, we got to be careful. There's two ways to handle this. We can think of this as, I was going to say negative 5, but we're subtracting. I'm going to keep the subtraction and think of this as 5 times negative 2, which is really negative 10. There we go. And keep the 7 there. All right. Technically speaking, we should multiply this, although sometimes it is okay to skip steps and do some of the steps in your head. That's within reason okay. So 3 times 4 is 12. Double negative means add, and then the plus 7. And technically speaking, we're supposed to add those two first, obtain 22. In fact, let me do that. 22, and then still add the 7, which is going to give us 29. In practice, oftentimes we skip some steps. So for instance, I would have probably skipped this one of the multiplication to get it 12. And probably once we have the 3 numbers, I would probably skip this one and just write 29. If you skip steps though, be very careful. You don't want to make a mistake. Yeah, we don't necessarily want to make a mistake, especially if we are taking an assessment, some kind of a test or quiz. Okay, C. G of x plus 1. Whoa. So now this is the formula. Remember what the formula says. Whatever the input, so there's a lot of stuff packed into this formula. Whatever the input, square it, multiply by 3, put it to the side. Or you don't have to put it to the side. While you're doing that, take the input again, multiply it by 5. Okay, once you have those two quantities, subtract them in that order, and then add 7. So there's a lot packed into this. So we're going to do that. Take the input and square it. Whoops. I put a 2 and it should be plus 1. Square it. Multiply it by 3. While that is happening, also figure out what 5 times the original input is, and then add 7. Okay, we have to square first. Remember PEMDAS? PEMDAS. So parenthesis, exponents first. So we have to take care of that first. So that is equal. See how I'm doing an equal here, indicating this quantity is equal to this. I mean, this whole thing, which is equal to this, which is, so that's what I'm doing here. I'm running out of space on this page, so I'm continuing the equation down here. So that is equal to 3 times, we're going to take care of the parenthesis and the exponent. So we're going to square that. I'm going to do that here on the side. Maybe I have room here. We're going to do x plus 1 times x plus 1. Of course, that is x squared. X times 1, x, 1 times x, x, 1 times 1, 1. So we end up with x squared plus x, 2x plus 1. All right, so that is the squaring, x squared plus 2x plus 1 minus, we're going to distribute the 5 with its negative, with its subtraction, onto the x plus 1. Minus 5x minus 5, and then we're going to add 7. Okay, now things get a little more complicated. This is a little complicated. It's not difficult, it's just complicated. Because technically speaking, we got to wait till we do this and then subtract this quantity, before we add the 7. But we have the associative property, which states, well, if we're adding and subtracting a bunch of things, we may want to take care of those if you want to. That's going to be 2. Negative 5 plus 7 is 2. So I might just as well simplify that instead of subtracting those 2, waiting until we obtain that, and then adding the 7 at the end. Even though originally it says, well, we should add the 7 last. Here, while we're actually working this out, we can say, wait, well, since we have the associative property, why don't we just take care of that since it's right there and not wait until we subtract, this quantity minus whatever this develops into. So we're going to do that. So we're going to do a few things in one step. We're going to distribute the 3 very carefully. So we have 3x squared plus 6x plus 3 minus 5x. And remember, negative 5 plus 7, 2. And then we simplify this by combining like terms. So we have 3x squared, 6x minus 5x plus x. And then 3 plus 2 plus 5. So this is the simplified output of g, which g? This g of x plus 1. By the way, a mistake, a really, really bad mistake would be to say, okay, so let me write down something down here. By the way, some students who do not know this may think of this very simplistically and say, oh, g of x plus 1, all I have to do is add 1 to g. G is 3x squared minus 5x plus 7. So add 1 to that, and that's going to give us 3x squared minus 5x plus 8, because we're just adding 1. So if we say that g of x plus 1 equals that, I have to say that that is very, wrong. We don't, we, yeah, that tells the teacher who observes this or whoever was watching this, if you did that, that that you don't know what's going on. That we just simply don't know. Now, not knowing is not a bad thing as long as we want to learn. If you want to learn it, but it's not knowing something is not necessarily bad by itself. Yeah. There's one more example that is almost too simple. The constant function. It's so simple we miss it sometimes. We miss what it is about. And so we did F in example 14. In 15 we used G. I want to stay with the alphabet, so H. H of X equals 8. That is called the constant function. So this is very important. So this is given. This is telling us that the input is not used in the output. That's a very, very important thing not to miss. See how this is telling us that the input is used twice in the computation of the input. Rather, in the computation of the output, the input is used twice. This example says the input is used once. The number of x's that show up in the formula tells us how many times we're going to use the input. So use it once. Use it twice. Don't use it. So the absence of the input x in this formula says don't use the input. Do not use the input. The output is eternally going to be 8. So what is h of 5? 8. What is h of 7? 8. What is h of 19? 8. What is h of 0? 8. What is h of negative 7? 8. Oh, what is h of 8? Guess what? 8. What is h of a pickup truck? Well, guess what? 8. Because don't use the input whatsoever. What is, whoops, F, G, H. So that's kind of weird. I'm using the letter H because I'm going down the alphabet, but we're still, so that H has nothing to do with this H. Those are two different H's, even though that was just a coincidence. But X plus 1. 8, don't use the input. Literally, that's what it says. It's implicit. If there's no X, that means that we are not using the input whatsoever. I, H of just about anything you want to put. R, the letter R. 8. Doesn't matter what you put in there, the output will be 8. It's so simple. It is confusing. And just one more, since we're talking about that, not to be confused with I. So this is an example. 17. I of x equals 8x. So again, this is given. Okay, so now you gotta watch out. I'm gonna pull out the same. So what is I of 5? My 5 sometimes look funny, but that's a 5. 40, why? 8 times 5 is 40. I of 7. That's the one that always gives me problems. 7 times 8 is 56. C, I of 19. Oh, why did I pick 19? 38. Well, 19 times 8, 72, carry 7, 152, if I didn't do this incorrectly. But let me jump down to another one. I of a pickup truck. It's not 8. The answer is not 8. It is 8 pickup trucks. So we got to watch out, because it's very easy to confuse this function with this one. That's the constant function. That's not the constant function. All right. I hope this is a good introduction to functions, and we'll stop here.